Okay guys, so we're going to do a little investigation here. I'm going to do the first part on the first page with you, and then you guys are going to do the second part on the second page. So our investigation is going to be to figure out what the derivatives of sine, cos, and tan are. So sine and cosine and tan actually are periodic functions. So what do you guys think might happen with the graph of the derivative function or with their derivatives if the original function is periodic? Periodic means it's like a repetitive pattern, right? Right, so if my function keeps repeating and returning back to the same values over the same interval, my derivatives, or in other words, the slopes of the tangents, will also follow a regular repeating pattern. So we could assume here that the graph of the derivatives will also be periodic. Okay, so in order to kind of investigate what the derivative of sine x is equal to, we're first going to just identify some points on the function. So we know that the regular sine function has some points marked off for us here. We're going to record the y values in this column. So at 0, we have a y value of 0. At pi over 2, we have a y value of 1. At pi, we have a y value of 0. And so on. So these are kind of like the key points that we were working with from sine last year when we were doing like graphs and transformations in radians. Can somebody tell me the points on the graph of sine x where the tangent will equal 0? Okay, pi over 2 is one of them. 3 pi over 2, and if we went into the negatives here, we would see negative 3 pi over 2 and negative pi over 2. And if we continued the pattern, we could imagine if it's 1 pi over 2, 3 pi over 2, the next one would be 5 pi over 2, and then 7 pi over 2, and so on. So it's odd multiples of pi over 2. So at least on our graph, we can see that these are the x values where the tangents have slopes of 0. Okay, and then we could continue the pattern to like 5 pi over 2, 7 pi over 2, and so on. Okay, oftentimes we would basically kind of like create like a negative number by saying like 2k plus 1. So odd multiples of pi over 2, where k is an element of the set of integers, which is this kind of like z with the double bar. Basically that just means when we say integers, we mean like whole numbers. So what makes an even number even? It's a multiple of 2. So what is 2k plus 1? It's a multiple of 2, which is an even number, plus 1. So it's 1 after an even number. So this basically just means odd. Odd multiples of pi over 2, and k cannot equal 0 here. Oh no, k can equal 0. Sorry, JK. So z is the set of integers, which is whole numbers. So any negative, 0, or positive number, as long as it's whole. Okay, so this is essentially just like a summary that says like odd multiples of pi over 2 is where our slope of our tangent will equal 0. Okay, so I know at pi over 2 and 3 pi over 2, the slope of the tangent is 0. So I'm going to put that in our chart here. Okay, identify the points on the graph where the slope of the tangent will be at a max and where the slope of the tangent will be at a minimum. So where is the slope of the tangent on this graph going to be the steepest in the positive direction? 0 is one of them, yes. So here, this is where the slope of the tangent will be the absolute steepest in the positive direction. What other? 2 pi, yep. And also at negative 2 pi, that's right. Okay, so we have 2 pi, 0, negative 2 pi. So we're at a max at numbers like negative 2 pi, 0, 2 pi. We could probably extend the pattern. What would be the extension of this pattern? What's the next one? 4 pi, 6 pi, etc. Okay, and where is the slope of our tangent at a minimum? Right, so this is like the steepest tangent in the negative direction. So we can see negative pi, pi. If we continue the pattern, what might be the next one here? 3 pi, 5 pi, etc. Okay, I could say for this one, we could say like 2k times pi. So even multiples of pi, where k is from the set of integers. Okay, and then for this one, we could say 2k plus 1, so odd multiples of pi, where k is from the set of integers. Okay, so even and odd multiples of pi is where these are occurring. Okay, now the question is, what are the slopes of these maximum and minimum tangents? Part of what we could make a bit of an assumption on is because this is a periodic function, can anyone make a connection for me between the slope of the purple tangent line and the green tangent line? What might we guess about these two tangent lines if this is like a perfectly kind of like symmetrical periodic function? Essay? Not reciprocal, close. Yeah, so one of them's negative, one of them's positive, right? And they'll both kind of have, so if one of them is 2, the other one's negative 2, right? That's kind of the idea. Okay, so what is that slope? That's the question. So we're going to see if we can estimate the slope of this tangent line when x equals 0 by basically doing what we did in grade 12, which was creating a really tiny secant line with an interval that surrounds 0. So here's what we're going to use. We're going to use 0 as one of the points, but I'm going to write it as 0 pi over 100. Basically, just because I want to find a really close number to 0, which would be 1 pi over 100. So really what we're saying here is like 0 to 1 pi over 100. Or I could use negative pi over 100 and positive pi over 100. You could use negative pi over 1,000 and positive pi over 1,000. We're just looking for something that's really close to 0, but like a tiny interval. So we're using this secant slope to figure out an estimation for the tangent slope, is basically what we're doing. So do you guys remember those limit charts that we did in advanced functions where we shrunk the interval closer and closer together, then we found the limit? This is basically what we're doing, but we're just making the interval small to begin with. Okay, so if we're estimating the slope of the tangent, for the function sine x when x equals 0, we know that this is approximately going to be equal to just the tangent or the secant slopes from y2 to y1 and x2 to x1. So using the slope formula to make an estimate here. Okay, so y2 and y1 are going to be calculated when sine is evaluated at each of these values here. So the sine of 1 pi over 100 minus the sine of 0 pi over 100 is just 0, right? I'm just kind of showing you guys that we're taking it like one little step forward from 0 pi over 100. So I'm just going to say sine of 0, and then x2 will be pi over 100, and x1 is, of course, 0. You can put 0 pi over 100 if that makes you happy, but it's really just 0. And then we're just going to calculate. So grab your calculators, make sure you're in radian mode. Yes. Okay, and I'm going to have you guys calculate this. Okay, so you should see like a little highlighted R or RAD in the top of your calculator. If you need any help while everybody calculates this, I'm going to come around quickly, okay? Raise your hand. Okay. Who has calculated this? What did we get?
0.999835515.
Okay, so you should get 0. Say it to me again, Michael.
999835515. We need to be that specific. Yes, Grace B. Rocket science.
Okay, so could we maybe make a guess as to what this is very, very close to? Okay, this is approximately equal to 1. So we could make a guess that our slope of our tangent when x equals 0 and negative pi and negative 2 pi and 2 pi and 4 pi and so on is 1. So I know here at 0, slope of the tangent is 1, and at 2 pi, slope of the tangent is 1. And we made a bit of an assumption about 0, this is how the slopes of the positive tangents relate to the slopes of the negative tangents. So could we make a guess on what the slope of the tangent is at negative pi and pi? -1. Okay, -1, very nice. Okay, so we've completed our column. Now we're going to graph the x points and the points of the derivative, okay? So we're going to graph that and we're going to see what we get here. And we'll make an assumption about the derivative. So we have the point 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. So I'm using these as my x coordinates and these as my y coordinates. Say that again, Alex.
Isn't that just the cosine function?
This is the cosine function. So the derivative of sine x is actually cosine x. Okay, so this is the cosine function. So we can see how the x values of the original function relate to the slopes of the tangents of the derivative function. And we actually get the cosine function. So this is the derivative of sine x. Okay, so you can make a final statement here that the derivative of sine x, this is what I labeled the graph with above, is equal to cos x. Okay, so you guys are going to complete the second part of this, and you're going to see if you can make a conclusion about the derivative of cosine x. Now, we know that the derivative of cosine x, or that the graph of cosine x is just a shifted version of sine x. So the slopes of where the tangents are at maxes and mins, like maximum slope of the tangent, minimum slope of the tangent, should be the same as the estimation that we just made for the slope of the maximum tangent. You can also make an estimation for minimum, but we kind of know that it's symmetrical, so +1 and -1. So this one should be a little bit easier. I'll give you guys a couple seconds. You don't have to do number 3 just yet. Okay, so we should have filled in for these the points for cosine, and we can make a conclusion that 0, pi, and 2 pi have derivative slopes of 0, okay, tangent slopes of 0. And we have a maximum slope of our tangent at 3 pi over 2, which we estimated in the last one was 1, and a minimum slope of our tangent at pi over 2, which we estimated as -1. We're not recalculating any of these because we already did an estimate in part 1, and sine and cosine are just shifted versions. So when we look at this, we can see that this is essentially a sine graph that's vertically reflected. So we can make a conclusion that the derivative of cos x is negative sine x. Okay, and then next we're going to see if we can find the derivative of tan x using the identity sine x over cos x and using quotient rule. So we're going to take a couple seconds to do that. So the first thing that you guys should have gotten here is derivative of the top. So this is the top prime. Derivative of sine is cosine times the bottom minus the top, just as it is, times the derivative of the bottom, which is negative sine x, over the bottom squared. So if we simplify this up a little bit, we have cos squared x. Negative and negative make positive. And we can write cos x squared, we usually just write that as cos squared x. And then we are going to apply an identity. Any idea what identity I'm going to apply here? Yes, this is the Pythagorean identity. We know cos squared plus sine squared is actually equal to 1. And 1 over cos x. I know this is 1 over cos squared x, but what is 1 over cos x equal to? So 1 over cos squared is secant squared. So the derivative of tan x is secant squared x. There we go. Okay, so this is where our derivatives come from. They're listed for you below as well, just so that you have them all together. And we're just going to apply them to a couple different questions today, and then tomorrow we'll get a little bit deeper into applying some of our previous differentiation rules into our new derivatives of trig functions. So here's our 3 derivatives that we're going to work with today. Okay, we're going to focus in on a few of our previous differentiation rules today. We're going to look at the constant multiple rule and the sum and difference rules, just to kind of ease our way into it. So the constant multiple rule basically just says if you have a constant multiple in front of something, keep the constant multiple. Guys, can you put it away, please? Keep the constant multiple and differentiate the function that's next to it. So for instance, guys, when you guys did something like, let's say 3x squared previously, we kept the 3, and then we basically just take the derivative of this function here, right? So we take the derivative of x squared, we get 2x, and then we multiply it together. So we're going to do a similar thing, but with our trig functions. And we are just going to basically keep the constant multiple and take the derivative of the function. So 2 stays, and then derivative of sine x is cos x. Yep, you're right. And that's it. Okay, so same thing here. Keep the constant multiple and then do the derivative of the function. So derivative of cos x, negative sine x. And then you're just going to simplify a little bit here. Negative and negative is positive 3. Okay, and then same thing here. You guys, I don't really mind if you're not calculating like the derivative, if your function is y equals rather than like function notation, you guys can use y prime. I do prefer, however, we're going to see in like a couple of these later questions that we have to evaluate y prime at a particular value. In that case, it's better to use dy over dx notation because then you can say when x equals whatever. But for ones like these where we're not using the derivative to calculate anything, you can use y prime. That's fine. Answer for this one, does someone want to help us out with this? Perfect. 4 secant squared x. Okay, any questions on that one? Pretty straightforward. Okay, sum and difference rules are basically just like for any multi-term equation. We just take the derivatives of each individual term here. So when you guys did something like 2x plus x squared, you basically, to find the derivative, just take the derivative of each of these terms. So that's what the sum and difference rules are telling us here. Just take the derivative of each individual term. So y prime for the first one, anyone want to try this one?
Cos x minus sine x.
It will be cos x minus sine x, that's right. Okay, and then second one. Anyone want to try this one?
Is it just negative 2 sine x minus 1 cosine?
It is.
Should we like factor that?
Yeah, I would say maybe we can factor the negative 2 here, and then we'll be left with this in the brackets. I won't be like super picky about this. However, sometimes when we common factor or when we look further, we might be able to actually apply an identity to simplify. So it's nice to common factor just to see if we can maybe simplify what's left in the brackets here. In this case, we can't. But yeah, always good to common factor. Okay. Find the slope of the tangent line to the graph of f at x, where at the point where x equals pi over 4. Okay. So slope of the tangent, we want to think derivative. So we're going to find f prime at x to start. So derivative of 3 sine x. What's the derivative of 3 sine x? Michael?
Cos x.
3 cos x. Very nice. And we are going to evaluate that derivative when x equals pi over 4. Okay, so we do not need our calculators. Don't grab your calculator, you don't need it. Okay? You should be able to calculate something like this. We have some special triangles that can help us with this.
Let's go. Jujitsu class.
Okay? We're going to leave these values in exact form wherever possible. So this triangle that we're using is the 1, 1, root 2 triangle. And so cosine of pi over 4, if we look at pi over 4 as one of our reference angles, this will be adjacent and hypotenuse. So what's the cos of pi over 4? 1 over root 2. Okay, so the slope of the tangent to the graph is 3 over root 2. We are going to try to simplify and express these with rationalized denominators if possible. So we're just going to multiply the bottom by root 2 and the top by root 2. And root 2 times root 2 is just 2 on the bottom. So this is what we should get. Okay, and then last one, find the equation of the tangent line. So this is a full equation in y equals mx plus b form for our function f at x at the point where x equals pi over 6. So for this one, we're going to end up using the triangle that has the pi over 6, pi over 3, pi over 2.
That's like the big one, right?
What do you mean by the big one?
The weird. Yeah, that one. Yeah.
Okay, so that is this triangle with sides 1, root 3, and 2. You can know which side goes across from which angle because the smallest side needs to go across from the smallest angle. So across from pi over 6, which is the smallest angle, should be 1. Across from pi over 3 should be root 3. And across from pi over 2 is 2. Okay, so the side lengths correspond to the angle measurements. Okay, so first things first, let's find the slope of the tangent by finding the derivative. Okay, our derivative here is negative 2 cos x, and we're going to evaluate that at pi over 6. Okay, so pi over 6 is our reference angle. That makes this adjacent and hypotenuse and opposite. So what is the cos of pi over 6? Root 3 over 2. Okay, the 2's here will cancel and we'll just be left with negative root 3. Okay, we also need a point on the line. So this is going to be our slope of our tangent. We need a point. We have the x, we need the y. So we're going to evaluate f at pi over 6. So same process that we've done in the past. The process isn't new, it's just the derivative part that's new. So sine of pi over 6. Use the triangle. What is the sine of pi over 6? Opposite over hypotenuse? 1 over 2. Very nice. The 2's will cancel and we're left with negative 1. So our point on our tangent is pi over 6, negative 1. Oops. Okay, so here's what we've got so far. In y equals mx plus b form, we have negative root 3 as our slope. And we can also plug in a point on the line. So we know that our point is negative 1 pi over 6. Okay, so I'm just kind of merging these two together and we're moving them to the other side here. You will see that some questions in the solutions merge these together with a common denominator. Some of them don't. I won't be too picky about that. We'll try to keep it in like simplest form. So like you can, if you want, you can find a common denominator here and you can express your b as like one whole value. Or if you want to leave it there, as long as it's like relatively simplified, like this part is simplified, then that's fine as well. I'm not going to be picky about it. So if you guys ask me like, when do you want me to do it? When do you not? I don't really care. It's up to you. So you guys can see in your homework, some of them will show you like, okay, here's how we would put it together and simplify into one fraction. Or we can just write it like this. And it doesn't really matter whether you put the negative 1 first or second, as long as the negative stays with the 1 and the positive stays with the pi root 3 over 6. Okay? So I would be fine with this, and I would also be fine if you want to express this as a single fraction. It's up to you.
Mr. Kalis,
Yep.
so we're getting marks for using the triangles, right?
I think we should know how to use the triangles. I want to see your process. I know that your calculator knows the answer. I want to know that you know the answer. So, yeah, I want to see your... Yeah, you can absolutely check with your calculator, for sure.